Good morning, everybody. Let's start with Module 4, Electronic and Digital Instruments. So let us have a look at the syllabus. Introduction, Essentials of Electronic Instruments, Advantages of Electronic Instruments, True RMS Responding Voltmeter, Electronic Multimeters, Digital Voltmeters, Ramp Type DVM, Integrating Type DVM, Successive Approximation Type DVM, Q meter, principle of working of electronic energy meter, extra features offered by present day meters, and their significance in billing. So coming to the introduction part, electronic instruments basically are defined as the instruments based on electrical or electronic principles for its measurement function. Now let us see the basics or essentials of electronic instruments. Any electronic instrument for that matter essentially must have a transducer, signal modifier, and indicating device. So an electronic instrument will have a transducer which will convert any physical or non-electrical signal into equivalent electrical signal. That is fed to a signal. The output of the transducer is fed to a signal modifier which makes the signal or modifies the signal to suit the requirements of the indicating instrument. So any electronic instrument will have a transducer, signal modifier, and an indicating device. Let us talk about the advantages of electronic instruments over the other type of instruments. They are fast in response, they are reliable and accurate, less prone to failure, they are highly efficient, they can measure most quantities as many physical parameters can be converted by transducers. So not only electrical signals, any non-electrical parameter also can be measured because we have transducer. The reading can be obtained in digital form and hence analysis becomes easy and can be recorded. So the readings so obtained after measurement can be stored and it can be displayed in digital format. So the transmission of signal also becomes easy and will not be losing any information. Next, electronic signals, since they are electronic in nature, they can be amplified, filtered, sampled, and measured. Electronic instruments are highly sensitive and their power consumption is less compared to other instruments. So these are some of the advantages of electronic instruments. Now let us go to the first one, which is true RMS reading voltmeter or 2 RMS responding voltmeter. So coming to the RMS value of voltage, we see in this instrument we can measure the RMS value of voltage. RMS is nothing but root mean square value. This is root mean square value of any AC voltage is any AC voltage waveform basically, or any sinusoidal wave is nothing but it produces the same amount of heat, or it is going to the quantity of AC wave that is going to produce the same amount of heating effect that produced by equivalent DC signal. That is nothing but RMS value of AC signal. So that AC RMS value we can measure using this instrument. So coming to the construction part of it, it contains an amplifier, AC amplifier, and another one DC amplifier for the purpose of enhancing the amplitude of the signal. Then we have a thermocouple. We have measuring thermocouple and balancing thermocouple. Thermocouple basically is a transducer. We very well know that transducer converts non-electrical signal or physical parameter into equivalent electrical signal. Here we have thermocouple, which is going to convert the heat into equivalent electrical signal, heat energy into equivalent electrical signal. Then we have an indicating meter, which is used for indication of the RMS value. So coming to the operating principle, initially we give the AC input and suitable amplification will be done by amplifier, and that will be connected to the heating element of the thermocouple. The heating element of the thermocouple dissipates energy in the form of heat, and since it's a thermocouple, that will be converted into equivalent electrical signal, and that is measured as V1 as seen here. And this thermocouple basically is a nonlinear device. So in order to compensate for the nonlinearity, we use another thermocouple called as balancing thermocouple. So balancing thermocouple and measuring thermocouple are connected in this, they are connected in this way as shown here, such that the non-linearity gets cancelled out. So the two thermocouples will form a balanced bridge to the input of DC amplifier. So we have the DC amplifier here. So initially you have V1 that is produced by measuring thermocouple, which tends to upset the balance of the bridge, and then that will be fed back to balancing thermocouple. So that feedback current will go to the balancing thermocouple, which produces heat energy that will be again converted into electrical signal V2, such that V1 minus V2 will be fed to DC amplifier. Now, let us go to the mathematical part of it. Let us try to realize that the RMS value can be obtained. So, for any thermocouple, output power is basically given by the expression P is equal to ERMS square divided by R. So, this can be written as P is equal to K into ERMS square. P is equal to K into ERMS square. Output power produced is always proportional to heat generated, which depends again on the output voltage. So E naught will be equal to K into ERMS square. So this is equation number 1. This is because power is proportional to output voltage, so we can directly write E naught is equal to K into ERMS square. So for measuring thermocouple, we can write the output voltage V1 will be equal to K into ERMS square. Input is ERMS, output will be V1 from the thermocouple. So V1 will be equal to K into ERMS square. Similarly, if you write it for balancing thermocouple, V2 will be equal to K V0 square. So if you observe here, the input for the balancing thermocouple is V0, output is V2. So V2 is equal to K into V0 square. Consider the DC amplifier. If you consider the DC amplifier, we know that output by input is equal to gain. So V0 is nothing but output. V1 minus V2 is input. A is the gain. V0 is equal to A into V1 minus V2. So V0 by A is equal to V1 minus V2. Generally, at balance, the gain of the amplifier will be very high, such that you can consider V0 by A close to 0. So V1 minus V2 equal to 0. V1 is nothing but equal to V2. So our expression for V1 is K ERMS square, V2 is K V0 square. So if you equate them, you get ERMS square is equal to V0 square, or ERMS is equal to V0. So from this, what we can understand is the reading that we get in the indicating meter V0 is a measure of input RMS voltage. So this finishes with true RMS reading voltmeter. Next, we have electronic multimeters. Electronic multimeters being pretty simple will be taken up later on. Now let us move on to the most difficult topic, that is digital voltmeter. Digital voltmeter basically displays the AC or DC voltage being measured directly as discrete numerals in decimals. So the reading given will be in digital form. Coming to the advantages of DVM, it will avoid the parallax error that we'll be observing in analog instruments. Response is quicker. Output of DVM can be stored in memory devices since being digital, accuracy is high. So coming to the block diagram of DVM, we have ADC, signal processing unit, data transmission element, display unit, and reference. So for any DVM, these are the main blocks involved. ADC is nothing but analog to digital converter. Then the signal has to be processed such that it will suit for the next stage. Data transmission element, where the data will be transmitted to the display device. And for ADC to function, we need a reference value that will be fed to ADC. So among the different types of DVM, we have successive approximation type DVM, linear ramp type DVM, dual slope integrating type DVM. So coming to successive approximation type DVM, So this is the block diagram which has comparator, D2A converter, reference, logic control and sequencer, and then digital display. So this basically works on null detection principle. That means if we take, for example, a simple vegetable weighing machine, if you consider the conventional one, the earlier one that we had, the unknown quantity of vegetables used to be put on one side and the known quantity of weight was put on the other side, and whenever the indicating instrument was reading zero, quantities on both the sides used to be considered to be equal, and the known quantity of weight was equal to the unknown quantity of vegetables, say for example half kg or 1 kg or so and so. That is called as null detection principle, where the quantities on either sides, if they are equal, sorry, the quantities weighing on both the sides, if it is equal, the indication reads zero or null, indicating balanced. So the same logic is applicable to successive approximation type DVM in order to measure the input voltage. So here we have the various blocks. Comparator basically compares both the inputs and declares high or low based on the nature of comparison. It is going to indicate high or low. You have logical control and sequencer block, which basically based on the logic being programmed, it is going to generate sequence of steps based on the reference input. Reference input for D2A converter will be generated by this reference block. D2A is going to convert digital to analog. Display unit basically is a 7-segment display unit used for displaying the measured voltage. So coming to the working, so initially the unknown input voltage to be measured is fed to the comparator, and when it is compared with the output of D2A converter. So here unknown input voltage is fed to the input of the comparator, and output of the D2A converter is also fed to the comparator. So whenever the two inputs are compared, if it is unequal, it will indicate high as the output, and it will be fed to logical control and sequencer. And then the D2A converter will generate the next sequence. Say for example, let us consider uh, yeah, the comparator compares the inputs and outputs logic 1 or 0, high or low basically, depending upon the logic control and sequencer. And then logic control and sequencer updates the sequence. Whenever the two inputs are unequal, it will update the sequence and feed it to the comparator. And this cycle continues until the two inputs are equal. And once the two inputs are equal, it will be declared in the digital display. So for that purpose, let us take an example here. Let us assume the unknown input voltage that we are planning to measure is 4.854 volts, for example. Then the logic control and sequencer generates 97531 in sequence one by one. It will be fed to a D2A converter and it is passed to the comparator. So let us see. Initially, the first one that we are going to send from the D2A converter is 9. So logic control and sequencer generates 9 that will be converted into analog signal and fed to the comparator. Now the unknown input, say for example, for our it is 4.854. So 4.854 will be compared with 9. So when it is compared with 9, it declares high. That is, our reference happens to be high. So obviously, once the reference happens to be high, that will be fed to the logic control and sequencer, and logic control and sequencer goes to the next step. It will generate 7 and it will feed 7 to the comparator. Again, since 7 is also higher than the 4.854, again it appends the logic control and sequencer. It sends 5 again high, same cycle repeats. Next it sends 3. Once it sends 3 happens to be low, so it will indicate low. So once it indicates low, then it will be incremented and it will send 3.5, and 3.5 will be compared. Likewise, until both the inputs are equal, continuously the sequence of codes will be generated. Once both the inputs are equal, the it will be sent to the digital display as the final measured value. So this is a trial and error procedure, and it is called as successive approximation. Next method is linear ramp type DVM. So coming to linear ramp type DVM, here we have following blocks: ranging and attenuator, input comparator, we have ground comparator, oscillator, gate, counter, output, ramp generator, sample rate multi-vibrator. And we can see a waveform here. Let us understand each of them. So coming to ranging and attenuator, basically attenuator is going to attenuate the signal or reduce the amplitude of the signal to suit the requirements of the next block. And input comparator is the comparator used here is an equality comparator. That is, only when both the inputs are equal, it will generate the output. And at the bottom, we have ground comparator, which is going to continuously compare one of the inputs with the ground. And since when both of them are equal, then only it is going to generate the stop pulse. Oscillator is going to generate the clock pulse. Gate acts like a switch in between. So whenever the gate is triggered, oscillator clock pulses will be driven to the counter. Otherwise, it will be blocked. And counter is going to count the number of pulses and it will be given to the output. And here we have a ramp generator. Continuously, a ramp signal will be generated by the ramp generator and it will be fed to the ground comparator. And the number of cycles initiated will be monitored by sample rate multi-vibrator. So here initially unknown input voltage is applied to ranging and attenuator. So this continuously uh, adjusts the unknown input signal to meet the requirements of input comparator. So continuously the ramp signal will be compared along with the ramp signal will be basically compared with the unknown input voltage. So at some point of time, the unknown input will be equal to the ramp value. So let us see the same thing in the waveform. Say for example, we take plus 12 volts ramp signal, sorry, 12 volts ramp signal. So it will start from plus 12 volts, goes to the 0, goes to minus 12, and again goes to plus 12, and this is how it is going to continue. So let us assume at one point ramp signal is equal to voltage to be measured. This is called as the point of first coincidence. So at that point of time, in the input comparator, when the ramp signal is equal to the unknown input, start pulse will be generated. Once the start pulse will be generated, it will trigger the gate and gate will open, and the oscillator which will be generating the clock pulses will be fed to the counter. Counter starts to count the number of clock pulses. Then this ramp generator will continue to vary. The ramp signal continues to vary. At some point of time, the ramp signal will be equal to 0 when it is crossing the x-axis. So at that point of time, the ground comparator will be active because the ramp signal will be continuously compared with ground or 0 volts. So at that point of time, when both the inputs are equal, it is going to trigger the stop pulse. That is called as point of second coincidence. So stop pulse will be given to the gate. So once stop pulse will be given to the gate gets closed and oscillator is no more connected to counter. So in this mean time duration between the start pulse and the stop pulse, counter would have counted the number of pulses. So the magnitude of count will be the output, that is the voltage. So here we can see the gating time interval between start pulse and stop pulse in the waveform indicated by small t, and then gate opening and gate closing. In between that, the number of clock pulses have been generated. So the magnitude of count basically equals the unknown input voltage. So this is nothing but linear ramp type DVM. Next we have dual slope integrating type DVM. So here op amp acts as a integrator. So this is dual slope integrating technique. We have an integrator, we have a zero comparator, that is ground will always be compared with the signal. We have the control logic block, we have a flip-flop 5 decade counter readout function, and we have a clock that is given to the gate here. So op-amp is used as an integrated, as I told you. Now coming to the operating principle, initially we have the counter with that is reset to 0. The counter will be reset. The counter which is counting 5 decade counter will be reset. So once the counter is reset to 0, output of the flip-flop also is set to 0 and fed to the control logic. Output of flip-flop is set to 0 and fed to the control logic. Once it is fed to the control logic, it will provide a signal to S1 to be set to position number 1, and the unknown input voltage is connected to op-amp, which integrates the input voltage. So the output of control logic will be fed to S1. It will be giving the signal to S1 such that S1 will be connected to position number 1. So the unknown input voltage now is applied to the op-amp, and op-amp is going to integrate the unknown input voltage. So during this time, the capacitor will basically charge to the maximum. Capacitor will basically charge to maximum value. And then the output of the op-amp is fed to the zero comparator, and it changes its state and gives signal to the control logic. So the output of this will be fed to the zero comparator. So zero comparator, when both the inputs are 0, it will not generate any signal. So one of them is non-zero value over here because the integrator has started to work. This gives the signal to the control logic, and then control logic drives the gate to open, and clock starts to generate the clock pulses, which will be counted by the counter. And this counting continues until 9999, and after this particular value, counter will be reset to 0, and carry pulse will be generated and fed to the control logic. At this point of time, once the counter reaches its maximum value 9999, it will be fed to the flip-flop. A carry pulse will be generated, which will be fed to the control logic and puts S1 to position number 2. Now switch S1 will be put to position number 2, which is negative reference voltage. So when negative reference voltage is connected, the capacitor begins to discharge, and during this discharge, it gets discharged. So after the discharge of the capacitor happens completely, the output of the op-amp becomes 0 and the gate gets closed. Now whenever the switch is at position number 1 initially, V out is given by minus 1 by RC integral 0 to T1 V in dt. So if you integrate this, you have minus V in T1 divided by R1 into C. Call it as equation number 1. When S1 is at position number 2, V out will be 1 over 1 R1 C 0 to T2 minus V reference dt. So if this is done, we get minus V reference T2 by R1 into C. Call it as equation number 2. So subtract 1 from 2. 2 minus 1, we have V out minus V out on LHS. RHS minus V reference T2 by R1C plus V in into T1 by R1C. So we have V in into T1 by R1C is equal to V reference into T2 by R1C. So V in is equal to V reference into T2 by T1. So V in will now be equal to V reference into T2 by T1. T2 can be substituted with N2 multiplied by capital T. So N2 into capital T, and similarly T1 time duration can be written as N1 into capital T. It gets cancelled out. So V in is equal to V reference into N2 divided by N1. So from this we can understand that magnitude of pulses generated during the interval T1 plus T2, if we know that particular value, that is N2 and N1, having known the reference voltage, we can calculate the unknown input voltage. So here in this particular case, during T1, time duration T1, capacitor charges to the maximum. During time interval T2, capacitor discharges completely. So it appears to be dual slope. So it's called as dual slope and we have an op-amp acting as an integrator. So it is called dual slope integrating type DVM. So this completes digital voltmeter and introduction to electronic instruments. Further, we'll continue in the next session video.